Hello, everyone. Welcome to our webinar on Innovations in Public Safety, the Key Role of LiDAR Technology. I'm Nick Davis, your host for today's webinar. I'd like to welcome our presenters, Dominique Plord of LeddarTech and Dan Sellers of DCS Technologies. Dominique's career has been at the very intersection of sensor technology development and autonomous driving systems, which has allowed her to develop both a passion for and a remarkable understanding of LiDAR technology and its many applications. At LeddarTech, and working closely with the product lines, Dominique conducts on-road testing of various sensor technologies, looking at edge classes and the effects that adverse weather conditions have on the performance of sensor technologies. She also leads research into various use case scenarios for LiDAR, such as those relating to vulnerable road users, or VRUs, and regulation standards pertaining to ADAS functions in the automotive industry. Most recently, Dominique worked closely on the LiDAR Pixel, LeddarTech's 3D flash LiDAR, which offers a 180-degree field of view specifically designed for ADAS and autonomous driving applications. Dominique joined LeddarTech in 2017 as an application specialist for automotive solutions after obtaining her engineering degree in geomatic engineering from Laval University in Quebec City. Dan Sellers' career in electrical engineering spans 3 decades, allowing him to have cultivated a wealth of knowledge and experience in model-based automotive control software design and development, software controls for heavy-duty transit bus and automotive drivetrain systems, advanced automotive electronic product design and development, and both automotive and military electronic control systems reliability assurance analysis. Dan joined DCS Technologies in 2008 and is currently the technical and product lead for the Pedestrian Avoidance Safety System, or PASS, which automatically decelerates buses and other vehicles to reduce collisions with pedestrians and bicyclists. Dan holds a Bachelor of Science degree in Electrical Engineering from Purdue University and a Master of Science in Electrical Engineering from National Technological University. He is also a member of SAE. Dominique and Dan, welcome. Folks, please be sure to use your Q&A widget to submit your questions. If we don't get through all your questions during the Q&A session, then a reply will be sent via email. Well, let's get started. Dominique, over to you.
Thank you, Nick. So hi, everybody. Thank you for being here. Please, as Nick said, note your question for the Q&A. It will be my pleasure and Dad's pleasure to answer you and to be able to exchange a bit with you. So now, starting, I want to do a bit of an overview of the subjects and topics I will explore today. So first of all, autonomous vehicles. I want to explain a bit how the autonomous vehicles are developing today, where we're at in the market. I want to have a bit of an overview of the weaknesses that we have in today's ADAS system, what can be improved specifically into these ADAS systems that we have into our vehicle at the moment. Is there new technologies that are coming to the market and that are market ready in the next few years? And finally, I will do a very brief overview of the LiDAR Pixel that is developed for ADAS. And I will do a bit of an explanation of different use cases and scenarios that we think is a good fit for the LiDAR Pixel. I'm starting here with a quote that I find very interesting. It's from Ford's Chief Executive Officer. He's saying that we overestimated the arrival of autonomous vehicles. I think that this is something that we hear more and more in the last few months or years. Autonomous vehicles are not quite ready at the moment. We thought it would be a bit earlier than that, but now we see that it will be maybe 5, 10, and 15 years later than we thought. So why is it taking more time? There's many reasons for that, different variety of hurdles due to why is it taking more time. So first of all, just the development time that it's taking. It's a lot more complex than people thought at the beginning, I think. Also, the technology readiness, the components readiness, the cost also of the components. So it's going down a bit with the years coming by, but it's still really expensive to develop those types of technologies. It's a really complex system. Also, I think the market adoption, people might not be completely ready to have these type of vehicles on the road. And finally, and I think it's the big one also, it's regulatory and legal aspect of it. it's taking a lot of time for laws to develop and regulation and to be able to enforce it. And this is also one of the reasons, I think, why autonomous vehicle, completely autonomous vehicle at least, are taking longer than we thought. There's many challenges and opportunities ahead of us, and I think if we focus on the short term, we need to focus on ADAS systems. So if autonomous vehicles are taking longer and are not there yet, we need to focus on what's coming in the next few years. And the ADAS system market is huge. It's supposed to be, the market is evaluated to be $81 billion by 2025. This is including all different companies that are included in this, OEM, tier ones, the components, suppliers and stuff like that. So it's really a big market, and we need to focus on the short term and how can we improve those ADAS systems. So there's a lot to do in terms of efficiency, the convenience also of the system, and how can we make those systems more safe. Because I think this is the main goal also of ADAS and autonomous vehicles, is to make the roads safer. This, I think, is an interesting quote also. So it's saying here that at least one ADAS feature is available on 92.7% of new vehicles available in the US. So this means that basically every new vehicle that is sold in the United States have at least a technology inside it, a new sensing technology inside it. So it just shows how big of a market it is. This leads me to talk about the weaknesses that we have in today's ADAS system. So if it's such a big market, and it will be still a big market in the next 5-10 years, I think there's some weaknesses that we need to look at and that we can maybe improve after. So the technologies that we are using at the moment have some drawbacks, of course. Then this will always be the case. So the ADAS system are performing really good, and they're improving year after year, but they don't work well in 100% of the situations. At the moment, radar and camera are the two main technologies that will be used for collision avoidance. This is my topic of interest for today. So I think collision avoidance is one of the biggest aspects of ADAS. I think it's really important for bicyclist safety, pedestrian safety, or just also vehicle safety. So it's really a big point where it's important for general safety around the road. And I think there's still a lot of pain points in this aspect of ADAS. So some of these pain points will be really inherent to the technology itself. So when we are thinking about camera, for example, there will be some difficulties when there's low visibility. So one of the main aspects will be when it's during, for example, the night, in sunset, when there's a lot of light contrast. So you see on the image here on the left, when you're exiting a tunnel, you have this really high luminosity contrast that it will make it really hard for a camera to be able to detect that there's something at the end of the tunnel. Also, pedestrian detection will be hard on some radars, so it will be difficult to sometimes detect smaller targets like children that will be crossing a street. A group of pedestrians also, it might be hard to be able to distinguish one pedestrian from the other, and the same thing here with a pedestrian that would be really close to a vehicle. Then it could be hard for this type of technology to differentiate those objects that are in front of you. And this is really inherent to how is the technology built and really the technology itself. So you cannot have high resolution with a radar compared to other type of technologies like a camera, for example. So they all have their drawbacks. Another one of them is the environment. So when you have really complex environment like construction zones, dirt roads, if there's a police doing the circulation, then how will your vehicle be able to understand this complex situation? And this is a part where, at the moment, radar and camera have difficulties to perform in 100% of these situations, basically. Here, I think this is an interesting statistic. It's saying that 75% of pedestrian fatalities occurs in the dark as compared to daylight, dusk, and dawn. So when I'm saying that cameras or sensing technologies have some difficulties working in the night, then this becomes a big issue considering that almost all of the fatalities with pedestrian and collisions avoid during the dark. So this is, I think, a big point that make it clear that we need to improve the ADAS system at the moment and make it sure that it can work properly in the dark, because just this, I think, is a really important point, and it would be a great way to improve safety on the road. Here is a study that was made by the AAA, the American Automobile Association. So they used 4 different 2019 vehicles. So they tested these vehicles with different scenarios, always following the Euro NCAP scenarios. And the result that they got, I think, is it's really, I thought the ADAS system in 2019 on vehicles were better than that, honestly. So here, the result that they got is at 20 miles per hour, a collision with an adult pedestrian was avoided 40% of the time. So I think that this is a result that might be okay for helping in collision avoidance and stuff like that, but it's still not a perfect score. And then when you use a pedestrian target, this number of collision avoidance was reduced to 11%. So it means that basically when you have a children crossing the street, almost all of the newest system on the vehicles will not be able to detect it. Now when you move speed a bit higher, now we're at 30 miles per hour, which is still not that high because it's only like 50 kilometers per hour. 3 out of 4 vehicles tested failed to reduce the impact speed by at least 5 miles per hour. So basically almost all of the models here that were tested hit the pedestrian at full speed. And finally, the evaluated pedestrian detection systems, they were completely ineffective during nighttime conditions. So this is another thing that I was saying earlier. So camera have some issues during the night, and it's clearly showed here in the study that was made. So now I talked about the weaknesses that we have in the systems, ADAS systems at the moment, but what can be improved? So I'm thinking mainly about 3 different topics or points. First one is technology, of course. We need to improve the technology or use different technologies also. Second one is the regulations and standards that can be also improved. And finally, the test scenarios, a bit like the one I was referring to by a Euro NCAP. So these are all the 3 topics I think that we can improve. Technology, I'm going to dive a bit deeper here later. So now for regulations and standards. So creating a regulation, it takes a lot of time. So it's a really long process to be able to enforce and create a law. It takes about 10 years or even more. And this is specifically in the automotive world. So I think that we need some improvement in terms of regulation and standards to make sure that it's more clear and that every companies or every OEMs is following the same type of rules, but it's taking more time. So of course, I think it will come and it's in the process, but we just need to be a bit more patient. There's already some regulations that are coming in the ADAS system world. So the first one, I think it's a really interesting one. It's the European regulation for mandatory blind spot information system on trucks. This is starting 2022. So basically, every new truck model will need to have a blind spot information system on their vehicle starting 2022 in Europe. So this is really a big deal because it's one of the first law or regulation that mandates new trucks to have this type of blind spot information system. Another one that came in 2018 in the United States is that every new vehicle sold needs to have a backup camera. We see this coming more and more, and I think it's also a really important safety feature in vehicles. So there are different types of organizations that are working for standards and regulations. There are some regional organizations. So for example, in the United States, there's NHTSA, there's the Federal Highway Administration. In Europe, there's the United Nations Economic Commission for Europe, so the UNECE. This is the one actually that was in charge of the regulation for blind spot information system I was just referring to. There's also more global organizations like ISO or SAE International. these type of organization will work not really on creating regulation, but maybe more trying to push some standards and try to make some equality between different manufacturers to make sure that there's some quality in what we are putting into our vehicle. And then there's the international consortium. So this, I think this is really important to have those type of consortium. I think it gives a voice to many companies and different parts of the world. So basically, this type of consortium will be formed of technology companies, of OEM, tier ones, a lot of different companies from different technology, but also from different parts of the world. So they can have their own point of view, and they really can have a say or their own words in the ADAS system and how it's evolving. So I think this really helps in having standards that are including more worst case scenario and real life scenarios that we see on the road. I was talking about Euro NCAP a bit earlier. So the study that I was explaining from the AAA, they based some of their scenarios on the Euro NCAP. So what is Euro NCAP for those who don't know? It's an organization that's managing car safety programs for new automotive design. So it's not creating regulation or standards, but it will be evaluating different cars. So it will have this 5-star rating system that we usually see. And it will help the consumers be able to compare vehicles easily and have them see if this model or this model will be safer, comparing different features or specification of the vehicles. So they're elaborating different test scenarios for different features of the vehicle. And one of their test protocol that I find very interesting is the AEB one, so for automated emergency braking. So they are testing different ADAS system on different vehicles and trying to see which one is the more performant, basically. So I think this is a really important organization, but there's some issues or weaknesses here. And I think the problem is that maybe the market is moving just too fast. So it's hard to update standards and documentation every year. And I know Euro NCAP is trying to do it, but the market is moving really fast, and you cannot update standards or protocols every 6 months. So this is why maybe it's falling a bit behind. And also, I think that real-life scenarios might not be well represented in the Euro NCAP scenario. And I think these are the 3 main points why. It's usually low-speed scenarios. So you saw earlier with the study that I showed, the tests were made at 20 miles per hour and 30 miles per hour. So these are not really high speed or real life speed where you could hit a pedestrian. Sometimes it's at a higher speed. Also, it's usually done in good visibility. So usually during the day, there's some Euro NCAP scenarios that will be done during the night, but then you make sure that every 10 meters or something, you have a lamp pole and make sure that you have a really good visibility, even if it's during the night. And also, usually it's simple scenarios, so a vehicle that's coming straight and then a pedestrian crossing right in front of it. So it doesn't consider what happens in real life, and sometimes it's a lot more complex than that. And here is an explanation or an example of a Euro NCAP scenario. This one is pretty recent. So basically, you have a vehicle coming in, and it can turn either left or right at the intersection. And on the other side of the street, you have a pedestrian that will be crossing the street following the yellow dotted line. So this is a really interesting use case, and it shows how you need to be able to detect pedestrians before turning. So here, for example, you would need approximately 80 degrees of field of view to make sure that you detect those pedestrians. So I think this is a good use case, but it's not a worst case or what happens really in the real life. And if we look at this image here, which is not from Euro NCAP, but just thinking about real life edge cases, if you're approaching an intersection and you stop here, and then you have a cyclist that is coming from the left or right at a pretty high speed, you need to be able to detect it before deciding to move forward or not. So here in this case, you will need a much wider field of view to make sure that you detect this cyclist that's coming. So these are types of real life edge cases that could be considered by Euro NCAP, but or not at the moment. And I think it would help having maybe safer ADAS system on the road. And now, just previously I was talking about the technology that needs to improve. So I talked a lot about radar and camera. These technologies are at the moment in vehicles, but there's also new technologies that are coming, and you probably see where I'm getting into here. So LiDAR, of course, they're evolving a lot. It's technology that's entering really the automotive market. It's been here for a number of years now on test vehicles and different type of vehicles that did some tests. So these, and maybe for 10 years now, but in the last few years, there was a lot of optimization in terms of size, cost, and performances. So now the LiDAR technology is more ready than ever to be implemented into the automotive market. And when we think about LiDAR, it should not be seen as a competitor of this technology. I think it's really a complementary offer to the market. So it's really a new approach of sensing, new technology. It's different from a camera or a radar, and I think it can really complement these two technologies well to just make sure that you have higher performances on your ADAS system and that you have higher level of safety for pedestrian and vehicle detection. And LiDARs can be really used in different mobility markets. So we usually see LiDARs in autonomous shuttles. We also see it in passenger cars and robotaxi. But it can also be used like in trucks, commercial vehicles. Also, industrial vehicles could be really useful for LiDAR using. So I think there's lots of mobility markets where LiDAR has value, and not only in fully autonomous vehicle, but also in ADAS system. So why is LiDAR necessary for ADAS? So as I was saying, it's really a complement of these two other technologies, and we can really see it in the diagram here on the right. It's really every technology has their point where, or their aspect where they're better than the other. And I think for LiDAR, we have a really good information in distance, so a really good distance accuracy of the objects that are around us. And we also have a good angular resolution. So LiDAR will help us precisely know where the objects are in the environment. And finally, it has night visibility. So I think this is a major important aspect of LiDAR, is that if you're during the night, camera will not work so good, and then radar will have some difficulty, for example, detecting a pedestrian, but then LiDAR will be here to complement these pain points from radar and camera. So this is really what I wanted to explain, is that they can really complement each other to make sure that you have a safer system and make sure that your ADAS system is having better performances than what we have actually in the moment. So this was all for my part, and now I will let Dan continue on his part. Thank you.
Thank you, Dominique. I enjoyed your presentation. Hello, my name is Dan Sellers, and I am the lead engineer for DCS Technologies Safety Products Development. Thank you for joining us today. Just a quick overview of DCS Technologies. DCS provides a design and consulting service to clients in the automotive engineering and defense avionics industries. DCS engineers bring over 100 years of experience in the design and test of high reliability electronic devices and systems, including 30+ years of direct heavy-duty powertrain system experience, providing technical engineering services to Tier 1 automotive manufacturers and component suppliers. While the state of ADAS in the passenger car world is working its way to adolescence, ADAS for transit applications is certainly in its infancy. Here at DCS, our engineers are developing ADAS safety systems for the transit bus industry. The product I will be discussing today is our Pedestrian Avoidance Safety System, or PASS, for transit bus. PASS utilizes LeddarTech LiDAR technology to detect, warn, and respond to hazardous interactions between vulnerable road users and a transit bus. Pass alerts and assist the operator to mitigate collisions while maintaining passenger safety. Today I'll be stepping through the following topics. ADAS for transit bus is similar to pass car but different. Choosing the best sensor technology for pass. Detailed overview how the DCS pass technology assists the transit bus operator and how DCS is utilizing pass in a transit bus application to enable ADAS test and safety standard development for the transit industry. ADAS for transit bus, pedestrian avoidance and passenger safety. Transit bus versus passenger cars, similar safety goals, but we have very different operating environments. Whether we are talking about passenger car or transit applications, we safety design engineers all have the same goal: minimize harm to the vulnerable road users and passengers alike. I'm sure that many of you in the audience have seen or own a personal vehicle with an array of safety features, which pedestrian detection and automatic braking may be one of them. At DCS, we recognize that the same safety technology should be available to the transit industry, particularly urban transit buses where bus to vulnerable road user interaction is very high. So let's face it, buses attract pedestrians. The U.S. Federal Transit Administration reported that in 2017, the transit bus industry suffered over 4,000 collisions, resulting in more than 16,000 injuries and nearly 100 fatalities. That's the driving force that motivated our engineers at DCS to bring vulnerable road user collision avoidance technology to the transit bus industry with PASS. Transit bus and passenger cars' primary safety goal is the same: to mitigate collisions with vulnerable road users. However, the operating environments of the two are very different. Passenger car safety systems are designed assuming restrained passengers, allowing for full force emergency braking at the last possible instant. Passenger car collision avoidance systems are certainly marketed and sold demonstrating that fact. Transit buses, on the other hand, have numerous unrestrained seated and standing passengers. This highlights the need to protect the safety of the vulnerable road users external to the bus, as well as the passengers on the inside of the bus. Striking the balance between ADAS collision avoidance and passenger safety is critical. DCS realizes that it is crucial that ADAS for transit needs safety systems designs that assist the operator, not replacing the operator, as seen in past car systems advertisements. Choosing the proper sensor technology for the application. DCS engineers evaluated many object detection sensor technologies as the basis for our detection during the design of PASS. Robust object detection and tracking algorithms require highly accurate distance measurements. In addition to accuracy, the sensor technology needed the measurement range to cover the transit bus operating speeds and scenarios. LeddarTech LiDAR products delivered on both accounts. We needed the flexibility of the sensing technology to address operational specific vulnerabilities such as A-pillar blind spots and areas directly in front of the bus that may be obscured from the operator's view. Think bike racks, bikes in a bike rack in the front of a transit bus. We were able to tailor both the horizontal and vertical fields of view from the available LeddarTech LiDAR configurations. We needed high reliability to survive and perform in the environment of a transit bus where weather extremes and high vibrations are the norm. We needed a small feature size to provide flexible mounting options. When mounting PASS in a retrofit situation, ideal mounting locations may have already been claimed by existing equipment. With no moving parts and small feature size, the LeddarTech M16 solid-state LiDAR brings an inherent level of robustness to operate when needed in challenging environments while remaining small enough to keep our space claim in check. We also needed to provide a cost-effective solution to transit agencies. Most agencies have very tight budgets. LeddarTech solid-state LiDAR provides an impressive performance per dollar ratio that allows us to give our customers a safety system that's affordable. I'd like to talk a bit more about detail about how PASS works and how it assists the operator by providing automated warnings and active vehicle deceleration to hazard situations. PASS is an SAE Level 1 ADAS safety system providing operator assistance. And then the challenging environments for the operator. The typical transit bus operator must deal with an array of factors competing for their attention in urban driving conditions. To help drivers avoid or reduce the severity of collisions with vulnerable road users, PASS informs the operator and automatically decelerates the vehicle when an imminent pedestrian collision is detected. The PASS-controlled deceleration rates are specifically designed to gently slow the bus, allowing time for the operator to use the primary braking system to bring the bus to a controlled stop. Again, striking a balance between external VRU collision mitigation and internal passenger safety. So the response time is certainly critical. Many studies have shown that the time an operator takes to react to a stimulus, much like a collision warning indicator, and initiate a brake apply is about 1 second on average. Longer if the operator is distracted or fatigued. During that second, a bus moving 15 miles an hour will travel 22 feet. At 25 miles per hour, the bus will travel about 37 feet. During that time, there's effectively nothing being done to mitigate a collision. Once the operator does become engaged, the result will most likely be a panic braking situation. The panic stop may result in mitigating or avoiding the bus to VRU collision, but what it has created is a dangerous situation for the passengers, especially standing passengers. This is where PASS steps in. PASS immediately and actively responds to a hazard and improves the conditions, providing the operator time and distance, reducing the need for a panic stop. When PASS calculates a VRU collision is imminent, the driver is warned and PASS will take an instant action to begin a safe deceleration process. What does this mean? 1, the distance traveled by the bus before the braking action begins, in the examples I gave earlier, are now less than a foot. 2, the condition that is now presented to the operator is one of a lower vehicle speed, allowing the operator to apply the brakes to finish off the stop under a controlled condition. Avoiding the panic stop helps to keep both the VRU and passengers safe. As Dominique pointed out in her presentation, there are gaps to be filled in ADAS standards. Currently, the standards that do exist are overwhelmingly intended for passenger cars. ADAS standards for transit buses, especially in North America, are nearly non-existent. DCS has been fortunate enough to be part of a team sponsored by the U.S. Federal Transit Administration and Pierce Transit of Lakewood, Washington, to evaluate advanced collision avoidance with automatic emergency braking technology integrated into urban transit buses. One of the main goals of the project is to collect system performance and operational data to lay the groundwork for ADAS test and safety standards for transit buses. To generate the needed data, system performance testing was approached in a scientific and controlled manner. Our team first created test scenarios baselined by adapting and augmenting existing Euro NCAP, automatic emergency braking, and SAE J3029 test protocols to align with transit bus operating conditions and environments. Test protocol modifications included lowering the test speeds of the vehicle and test targets appropriate to typical transit bus operational speeds. New test scenarios were created to include turns with a vulnerable road user occluded by the A-pillar, simulated bus stop entry and exit, low light night conditions, and adverse weather conditions, rain and fog. In all, over 150 different test scenarios were executed on a closed area test facility. We are also currently collecting real-world system performance operational data on actual transit routes. The high-resolution data collected will be shared with the transit community to establish and improve operational procedures and processes. DCS is very excited to deliver ADAS safety features to the transit industry's the past product. This concludes my presentation. Thanks for the time, and back to you, Dominique.
Thank you, Dan. It was a very interesting presentation, and I think it's a good application, and it really shows where we can use LiDAR and ADAS systems. So now I want to do a really brief overview of the LeddarPixel Cocoon LiDAR for ADAS. This is a new LiDAR product developed by LeddarTech, and this is not supposed to be kind of a market push. I just really want to explain some use cases that we've thought about on our end. So this is what my team and we do, just thinking about real life scenarios and trying to develop a product that will have a real fit in the market. So this means trying to really understand the scenarios, the system requirements, and then this leads to final LiDAR requirements. So we're able to develop a LiDAR that we think will have a real fit in the world. So I'm going to try and explain a bit that. So first of all, the LeddarPixel, so what is it? It's a 3D flash LiDAR. It's 100% solid state. That's what we do here at LeddarTech. It has zero dead zone proximity coverage in all the illuminated field of view. So basically, this is the concept itself of a flash LiDAR. It's road-ready design. It also has superior durability. So we have a field of view of 180 degrees, so we're able to detect objects and VRU detection on all this horizontal field of view. As I said, it's the 3D flash illumination technology. This means that we have 100% scene coverage on all the illuminated field of view. And it's also based on the LCA2 LiDAR engine. So basically here at LeddarTech, we do LiDAR product. We also do SoC development. So the SoC and the signal processing library that we develop here is embedded into this LiDAR product. So what I want to explain is different scenarios that could be really type of real life scenarios. They are based from customers' feedback, from Euro NCAP standards, from other organization standards also. So it's kind of a mix-up of different things that we try to analyze. So first here we have pedestrian front collision avoidance. This is really basic or simple scenario. So you will have a pedestrian, NCAP type of pedestrian that would be crossing the street. Your vehicle is at 40 kilometers per hour. And then you have a deceleration of 3.5 meters per second square. And also you have a reaction time of half a second, so 0.5 seconds of reaction time. These values are important because they will tell you what is the detection range that you need on your system to be able to detect an object and then be able to stop your vehicle safely. So here with those values, we have a range that we needed to avoid the collision of 23 meters. This is calculating the stopping distance of the vehicle. And then on the LeddarPixel product, we have a range on a pedestrian of 30 meters. This just shows that. So we try to analyze these scenarios, and then afterwards we develop the product. So we analyze different scenarios, and then we say, okay, so we need these type of performances to make sure that the LiDAR that we push to the market will make sense and will really answer a certain need. So this just shows that we can comply with this first scenario. Here we have another one that it's kind of the same thing, but here we have different targets, and we also have a higher speed. So now we are at 60 kilometers per hour of speed, and then we have a reaction time of 0.5 seconds again, but then the deceleration is a bit more aggressive. So we are at 7 meters per second square. This would really be kind of an automated emergency braking, considering that you are in a vehicle and you have your seatbelt on, of course. So we have two scenarios, a cyclist that is crossing the road at 20 kilometers per hour, and then a running pedestrian at 8 kilometers per hour. And the range that you need to avoid the collision with both of these road users are respectively of 33 meters and then 28 meters. This is all done on calculation of the speed of the object and then the speed of the vehicle. So then again, on the Pixel, we have a range on the cyclist of 50 meters and on the pedestrian of 30 meters. Now this is the image I just showed earlier, and I thought this is kind of a real life edge case scenario. So you have a cyclist that's coming at a certain speed directly on your right, and then you are stopped at an intersection. So here you would need more than 160 degrees to make sure that you can really detect the cyclist that's coming really close from you. So with the pixel, we have, as I said earlier, 180 degrees of horizontal field of view. And then we have, again, the range on the cyclist also of 50 meters. So this use case would be complied. And last one here is a cyclist that would be along the road and a truck directly on its left, and that is going right in front of the cyclist and then making a right turn just in front of the cyclist. This is a really important use case. It's one of the use cases where there's most cyclist fatalities in the world. So trucks have huge blind spots, and this is exactly why the reason why they developed this new regulation that I talked about earlier. So the United Nations Economic Commission for Europe, they came up with this new regulation for blind spot information system, and this is the main use case behind it, so to be able to avoid a collision with a cyclist. So here I really used their numbers. We have a speed of a vehicle of 30 kilometers per hour, and the cyclist is at 20 kilometers per hour, and it's right behind it. And then the acceleration capability of the truck is considered at 5 meters per second square, and the driver's reaction time here is a bit longer. It's 1.4 seconds. The reason behind it is that this is an information system, so the truck will not brake by itself. The ADAS system will give a warning to the driver, so the driver needs a bit more time to look at its surrounding environment and then make a decision. So if we analyze those specifications of the scenario, we will need certain system requirements. So the detection range on the rear would be 30 meters. On the front, it would be 8 meters, and on the side, up to 4 meters. So this gives us kind of a 180-degree detection zone with a certain range that we need to respect to make sure that we comply with this scenario. And again, we have 180 degree on the pixel and 50 meter on the cyclist. So this pretty much concludes what I wanted to explain, just trying to think about real life scenario, what's going on in the real world, and making sure that we are developing the best product that we can to enhance safety on the road. So I'm pretty much done on my part, and I think we can move to the Q&A now.
Okay, well, thank you, Dominique and Dan, for providing that great overview. So let's now go ahead and dive deeper and begin our Q&A session. The first question looks like this one's for Dan. The question is, since PASS is a safety system, do you have the capability to provide system telematics information to the end user?
Yes, thanks, Nick. Yes, we do. PASS currently logs system performance and vehicle dynamic data during key events such as collision warnings and automatic emergency braking activations. We'll take those data logs that are transmitted back to our DCS servers from each vehicle for further analysis and distribution to our customers as needed.
Okay, great. So the next question, and this one looks like it's for Dominique. It's the question is LeddarTech doing development of LiDAR only, or is LeddarTech doing development of LiDAR with cameras and radars in a fully integrated solution? Okay, so at the moment we are really a company focused on LiDAR, so that's what we're developing. But of course, as I explained, cameras and radars will closely complement this LiDAR technology. So we're really looking into trying to have a closer communication and be able to really have an integrated solution with these other technology providers. So we work closely with our customers to make sure that they have a fully integrated solution, and we're really looking to improving this side even more. Okay, very good. The next question is for Dan. What, if any, are the minimum vehicle requirements for PASS?
Primarily, we are installed on transit buses, so we'll need a source of power, so a 1224 volts. We work on any of the voltages available on a transit bus, ignition input to turn us on and turn us off. We also utilize a handful of vehicle-specific operating parameters that we gather from the existing J1939 link, so the vehicle will have to be of the age where 1939 is available on the vehicle, which is from 1990 on, I believe. So most vehicles.
Okay, very good. The next question, again, this one looks like for Dan, maybe a comment and or a question. It would be interesting to know if a product like the Pixel could be incorporated into the PASS solution and what it would bring. So maybe if you could just comment on that.
Sure. With our system, we've successfully utilized the M16s as our current sensing device. With that said, our engineering staff has designed PASS to take advantage of in the latest advancements in any sensor technology. We've created interfaces to allow us to integrate with different technologies, and we would be very interested into evaluating the features of Pixel once we have the ability to, or the chance to evaluate that product.
Okay, great. The next question also looks like this one is for Dan. Is PASS compatible with existing fleet vehicles?
Yes, our engineers have worked pretty hard to ensure that we're compatible with a wide range of transit bus platforms, different manufacturers, OEMs. We've successfully installed on multiple OEM platforms to date as retrofit installations, so yes.
Okay, the next question, what is compared certainty of objects detected with solid-state LiDARs and mechanical LiDARs, and do we have any difference in reliability of results in real conditions?
Okay, I can take this one. I'm not quite sure I understand what is meant by compared certainty, but if we just think about the solid-state LiDAR that we are developing here at LeddarTech compared to mechanical LiDARs, well, basically, we use flash solid-state LiDAR, so it's different components. There's no moving parts. There could be more durability. Also, specifically the LiDAR that we do, so for example, Pixel, it's a flash LiDAR, so we are illuminating completely the scene, a bit like a camera would do, compared to mechanical LiDAR that will probably more shoot specific points in the scene. So it's a bit a different approach. We have no gaps in all the illuminated field of view, so we make sure that we don't miss any object that would be in the scene. So I think that reliability of results in real condition, it really depends on what we're looking into. For flash LiDAR solid state, we just make sure that we don't lose any object, and even a small object would not fall into a gap. So I think this could have a higher reliability result in terms of real condition, but it really depends on what we're comparing here. That would be my answer.
Okay, thank you. The next question looks like this one might be for Dominique as well. Are there significant differences between LiDAR sensor requirements for mass market passenger vehicles and autonomous vehicles, such as shuttles?
Yeah, great question. So I think mass market passenger vehicles is really different from autonomous vehicle like shuttles. So if you have a mass market passenger vehicle, you really need to have a safe system, automotive grade system. It also needs to be affordable, small size for seamless integration. So basically, you need to put it in a vehicle that someone will buy in the end. And then when you think about shuttles, then you might have more flexibility. So usually it will be higher level of autonomy, but it will also mean maybe more budget, more space. There's also a lot of differences in the requirements of the system, just into the levels of autonomy. So if we think about mass market passenger vehicles, we could develop an ADAS system that will be level 1 or level 2. So then we could need maybe only a radar for a specific application. And then if we think about a completely autonomous vehicle, of passenger car, then we need all of the sensor suite. So it's really different markets and different level of autonomy also that can be targeted. So yeah, that would be, I think, my answer.
Okay, great. Thank you. The next question, what are the main differences between mechanical scanning LiDAR and solid-state flash LiDARs for ADAS and autonomous vehicles? And do you foresee solid-state LiDARs completely replacing mechanical scanners in the long run?
Okay, I talked a bit about differences between mechanical and solid-state earlier, but then the end of the question is also interesting. So do I foresee, like basically, could the solid-state replace completely mechanical LiDAR? I think it really depends into the market we're looking at. So of course, when we're moving into higher level of autonomy, of course we need the LiDAR. So this is a no-brainer. But if we are able to have solid-state flash LiDAR or solid-state LiDAR that will have even higher performances than mechanical LiDARs, then of course I think these technologies will replace the mechanical LiDAR that can have more components that are less reliable or that have lower MTBF. So if we're able to achieve this level, then I think, yes, we could replace mechanical LiDAR, but it really depends also on the applications that we are looking into.
Okay, very well. The next question, what do you find the most challenging when trying to reproduce real-life scenarios for LiDAR testing?
Okay, yeah. I think well, for our part here, so we do a lot of LiDAR testing, of course, with what we're developing. And what's the most challenging is variability of the scenarios. It's hard to have a consistent test that we can do in the real life because there's so much different type of materials. I mean, if you have a certain color of car versus another one, or if a pedestrian is dressed this way versus another way. So when you really go into the real world and try to do some testings, every result will be different. If you choose a rainy day, a sunny day, a foggy day, all the results with your sensing system will be different. So it's really hard to have these conclusions that you get or these performances of your system that you can conclude that you have because of the uniformity or, in fact, the non-uniformity of the testing that we do. So we really need to rely on some standardized things. But if we want to go into real life and do some real life tests, then it's much more complex to do some analysis. And that's really the complexity, I think, of autonomous vehicle in general.
Yeah, can I jump in a little bit on this one too? We found this to be exactly how Dominique describes when we are running tests on an actual vehicle on actual transit routes, that there are many environmental issues that come up that are just difficult to simulate. So it's imperative to not only have standardized testing, which gets you a baseline, but to run many miles and tests on real life situations, and then analyze those situations to refine algorithms and scenarios.
Okay, very well. Thank you both. The next question is, what's your methodology for testing these new LiDAR systems in real life?
Maybe I can jump on it, and I think you might have also a point of view on that, Dan. But so as we said, it's hard to go into in the real life and have some precise analysis or conclusion because everything is just moving every day, and it's really not consistent. But we need to have this baseline, as Dan said, and we're using some standardized reflectivity targets. So there's many companies out there that are developing some products that will have certified reflectivity of specific targets. So it could be like 5% reflectivity, 50%, 80%. And then we can also use pedestrian targets, vehicle targets that are based on Euro NCAP type of standards. So we can buy these targets that companies made And then we make sure that when we go to a customer, or then when a customer tries different type of technology, they can use these type of standardized targets to test our product. So this really helped us to have this kind of baseline of performances of our LiDAR.
Yeah, and I would echo my answer to the previous question. It's just miles and time and just lots of engineering work to overcome your real world situations.
Okay, great. The next question. I would like to have more explanations on the scenarios and use cases analyzed in this presentation. On what did you base the parameters and values used in these analyses?
Yes, so I explained, there was a lot of numbers in what I explained here, and some of them were based on recognized standards. So I used a lot of numbers from the scenarios from Euro NCAP, the AEB validation protocol. Another one I said quickly was based on the United Nations Economic Commission for Europe. These are the ones that developed the regulation for the blind spot information system on trucks. I also used some numbers just from some customers that we're talking to, and then they use these values, and then we talk to different customers and they use the same values. So we kind of get this type of standard value that's not really official. There's also a lot of materials from AASHTO, which is the American Association of State Highway Transportation. They have lots of documentation that help us also develop these type of use cases.
Yes, we also used the Euro NCAP AEB protocols as a basis for our testing. Again, transit bus is a much different operating speeds than passenger car does. So some of the values in the NCAP are invalid for the testing that we were trying to accomplish. So that was a basis for a lot of our tests, and we expanded upon those scenarios to create tests that were valid for transit. We also used the J3029 from SAE, which is a vehicle-to-vehicle for truck and bus test. It's a relatively short tests for vehicle-to-vehicle interactions. So, but we really are trying to expand the standardization of testing for transit itself.
Okay, perfect. Thank you. The next question: do you think one technology is more important than the other between radar, camera, and LiDAR?
Oh, this is a great question. I think it's a question that we get a lot. So I think that there's not one technology that's more important than the other, especially when we're thinking about higher level of autonomy. Then if we want a level 5 or a self-driving vehicle, we absolutely need all of these technologies. So we need radar, camera, LiDAR, but each of them have their weaknesses, and then they can just help each other when we combine these technology. Of course, when we're thinking about lower level of autonomy, like level 1, level 2, we see a lot of systems at the moment that use sometimes only radar, sometimes only camera, ultrasonic also for help in parking or stuff like that. So you can have only one or two of these technologies, but I think when you want to have the complete system fully autonomous, then you will need every single technology.
Okay, well, great. It looks like we are out of time right now, so no more questions. I do want to thank you all for attending, and a special thank you to our presenters, Dominique Plord and Dan Sellers. So thanks again.
Thank you very much.
Thank you.